I'm Thomas De Silva, an engineer at Salesforce, and I work on the Apache Phoenix project. And I'll be presenting solving metadata management bottlenecks along with Rahul Gidwani from Yahoo. So the goal of this talk is to present the work we did to allow system.catalog to split so that it can span multiple regions. Currently, system.catalog is system.catalog is the table, is a Phoenix table that's used to store metadata about uh, tables and views, and it's currently you're not allowed to split it, so it's restricted to a single region. So here's an outline of the talk. I'll go over some background that details how Phoenix's data model works and how we store metadata in system.catalog. Then I'll briefly go over two use cases of Phoenix at Salesforce, big objects, which are used to store billions of rows in Salesforce, and also queryable reports, which are used to basically which store report data in Phoenix and HBase to reduce the load on our RDBMS system. Then I'll talk about the motivation, like why we want to allow system.catalog to split in the first place. Then we'll talk about how system.catalog is currently implemented, and then describe our new implementation that supports multi-region system.catalog. And finally, I'll talk about a few metadata optimization techniques. So we have update cache frequency and append only schema that can be used to reduce the number of RPCs to the system.catalog table. And then also auto partition sequence, which is kind of a helper technique that you have when you create views. So this is Phoenix's. So we all know that HBase is a sparse distributed sorted map. So it's sparse, meaning different rows can have different numbers of key values. So in this example, the first row has one key value from qualifier 1, and the second row has two key values, one in qualifier 2 and one in qualifier 3, but it doesn't have a key value in qualifier 1. Also, the column qualifiers are grouped into column families and they are stored together on disk. Phoenix supports composite row keys, so you can have all the key value columns are all the column values of the primary key columns are appended together and are used to generate the row key, and all the remaining column values are just stored as key values in HBase. So here's an example for server metrics data. Here in this schema, you have two primary key columns: host, which is a varchar, and date, which is a date. And the column values for the values for these two columns are appended together to generate the row key. And then you have four regular columns that are of type integer. So here's the DDL statement for the previous schema. So here you can see that we are defining a primary key PK on the two primary key columns, host and date. And since date is a fixed length column, we need to define it as not nullable. And then we have the remaining four regular integer columns. So here's how the data looks like in HBase. The host and date column values are appended together to form the row key. And then this picture just shows the first two regular columns, response time and GC time. And some rows have values. Some rows have values set in them, and some rows don't. So I'll talk about Phoenix views briefly. So HBase performs well if you have a few hundred physical columns. It doesn't really perform well if you have a lot, more than a few hundred physical columns. So to get around this, you can use Phoenix views, which create a virtual table that share the same physical table. So the views are used to refer to a subset of data from the parent table that is defined in the where clause of the view DDL statement. So when you define a view, you can add your own columns and extend the primary key column of the base table. So in this example, we have a base table event that has two PK columns, type and event ID, and two regular columns. And in the create view DDL statement, you can see that we have added a PK column referrer, and then a regular column created date. And in the where clause, we restrict this view to only include those rows where type is equal to W. So this particular view is updatable because the where clause contains just ANDed equality, a simple equality expression. So when you say it's updatable, when I say it's updatable, it means that you can use this view in a upsert query, and Phoenix will automatically set you don't have to specify the value for type, it'll automatically set it to W. You can also create an index on a view, and this is useful to speed up query performance. And all indexes for views are stored in the same physical HBase table. There are a few limitations that you need to be aware of when you use views. The first is they can only be created on a single table. So you cannot create a view statement that uses join to combine data from multiple tables. And views inherit all the columns of the base table. So if you see here, we always have to, in the select part, we cannot refer to a subset of columns from the base table. You need to always inherit all the columns from the base table. However, after you create the view, you can drop non-PK columns that are inherited from the base table. When you do this, then the view is marked as diverged, and if you add any new columns to the base table, they aren't propagated to the child views unless they are PK columns. Another restriction is you cannot drop a column that's referenced in the view where clause in the view. And if you have a view index, it's only maintained if the updates are made through the view. So if you upsert using the view, if you upsert using the base table, then the indexes are not maintained. So for the view event, for the base table event, here's how the data looks like in HBase. Since the event type is the leading column of the row key, all rows of a particular event type are stored contiguously in the table. So here you can see we have all rows from chat event stored together, and then mobile event, and then phone event and web event. And they are all ordered according to the leading column, which is type of the row key. So another feature Phoenix provides is multi-tenancy. So you can mark a table as being multi-tenant by setting the multi-tenant is equal to true table property. And when you do this, then the first PK column is used to denote the tenant, to identify the tenant, basically. So here, tenant ID, which is a varchar column, is used to denote the tenant ID. Along with so in order to use multi-tenancy, there are two things. You need to define a table as being multi-tenant, and then you need to use a tenant-specific connection. In order to create a tenant-specific connection, you set the tenant ID property at connection time. So in this example, we create a properties object, and we set the tenant ID property to tenant1, and we pass the properties along to the driver manager, and we get the Phoenix connection. And when you use a tenant-specific connection, you can only query global table data, or if the table is multi-tenant, you can only see rows in the table that belong to the tenant that belong to the specific tenant. And also, if you create any tenant-specific views, then you can only see the tenant-specific view that was created by the particular tenant. So how do you create a tenant specific view? First, so for the example we have here, here's the base table event, and we can create a view on this event table based by filtering on the type column. So here we create a web event view where we added two columns. One is a PK column, and we filter on type is equal to W. Then if you create a tenant-specific connection, you can create a tenant-specific view by just uh, creating a view on the global view. So the data in HBase for multi-tenant tables is, you can see that since tenant ID is the leading part of the PK column, all data belonging to a particular tenant is stored contiguously. So yeah, and since for the given example, the second column is the type. So for a given, so for all rows for a particular tenant, they are again ordered by the type. So as before, we are ordered by the particular views that we created. Like if we had created a chat event, a mobile event, it would be ordered. All of those rows will be stored continuously. So if you create a view on a base table, you can create multiple views on a base table, and those views can have child views of their own. And each view always inherits all columns from its parent. So over here, if you go to the leftmost view on level 3, you can see it inherits all columns from its parents, and it can also define its own columns. So a few of the use cases of Phoenix at Salesforce. First one I'll talk about is big objects. So big objects are similar to standard Salesforce objects, except that they provide consistent performance for billions of rows, which you cannot do with regular Salesforce objects. They support a subset of Salesforce SOQL, which is Salesforce's query language, and they do that by running Phoenix queries underneath. They only support a subset of features because we store this data in HBase. There's no support for transaction or triggers. Every big object corresponds to a tenant-specific view, and we have thousands of tenants which can have up to 100 big objects types, so we need to support millions of views. So here's the example. Here's an example object definition detail for a customer interaction big object. So let's say you want to track all the interactions a player makes in one single session of a video game. Then you could use this big object. It has different fields like date of play, if the player made any purchases in the game, the level achieved, lives used in the game, and other fields. So how this actually works is we have a base table for the big object that has two primary key columns, tenant ID and entity ID, and then two regular columns, created date and created by. So created by is used to see which user created this particular big object. And an entity ID is used to uniquely identify the type of the big object. So this is the base table, and then we have a tenant-specific view that inherits all the columns from the base table and also defines the columns. So every field of the big object becomes a column in the tenant-specific view. The next use case we use Phoenix at Salesforce for is queryable reports. So these reports initially the RDBMS at Salesforce is queried for data the very first time the report is generated, and then we store the data in a tenant-specific view. Subsequently, when you load the report, we don't query the original RDBMS, but we just query the view. And the reason we do this is to reduce load on our RDBMS. We also want to query a snapshot of data and not the live data. And we want to allow users to slice and dice the data however they want. So if they want to sort a group in a particular way, then you can't really just store this data in like a blob or a file. Phoenix allows you to just run queries on the view. So that's how we support this feature. There are about 100,000 monthly active users for this feature and about 10 million monthly active reports. And so each of these corresponds to a single 10 specific view. And so we need to support millions of views. These views are relatively short-lived, so maybe like a few days to a month. So what we keep seeing is the size of system.catalog keeps increasing until we run a compaction and remove the views that have been deleted. So here's how one of these reports actually looks like. This report is run on the opportunities for a particular org, and it has fields related to the opportunity like average amount and sum of annual revenue. So underlying, we create a base table that is called that's report instance that contains two PK columns, tenant ID and report ID, and one column is row number just to store the number of rows in the particular report. The report ID is used to uniquely identify. I mean, the combination of tenant ID and report ID is used to uniquely identify the report. So whenever a user creates a report, we create a view, a tenant-specific view on the report instance base table. It inherits all the columns from the base table, and then the fields in the report become columns in the tenant-specific view. So I'll talk about how we store Phoenix metadata in system.catalog currently. So every table or view corresponds to multiple rows in system.catalog. So the first row is the header row that stores information about the table, like the number of columns, the table type, whether the table is sorted or not, and any other table properties. Then you have linking rows. So if you have a base table that has 10 child views, you'll have 10 child linking rows to connect the base table to all its children. And similarly, if you have a child view, then you have a single row linking it to its parent. Then you also have the column rows. So each column corresponds to a single row, and we stored columns related information like data type, whether the column is nullable, and the sort order, etc. So basically, if you have millions of views, each of them can correspond to multiple rows in system.catalog. So you could have several billion rows in system.catalog. So for the report instance base table that we saw earlier, this is how the rows look in system.catalog. We have one header row for report instance, and here you can see the table type is view, which means it's a table basically. And then we have one child linking row that links the report instance to the view, which is the leaderboard view that was created earlier. And then you have three rows for the columns, the tenant ID, the report ID, and the row number. So this is the metadata rows for the tenant-specific view. You have, again, one row for the header, and you can see the table type is V, which means it's a view. And then you have one parent linking row. And then you have a row per column. So you have 5 rows for the columns that are created in the view, and then you have another 3 rows for the columns that are inherited from the base table. So the reason we need to allow system.catalog to split basically is we need to support millions of views that have, and each view corresponds to multiple rows in system.catalog, so we need to support billions of rows in system.catalog. Also, another thing that this will allow us to do is we can move the view metadata to a separate physical HBase table, and we can turn replication on for this table. Currently, system.catalog is not replicated because if you turn replication on and if you upgrade either the DR or the primary cluster, then then automatically the body gets upgraded even though you haven't actually upgraded Phoenix. So I'll go over the current implementation of how we add a column or drop a column to a parent table. So initially we lock the header row of the parent and all its children. And then let's say you're adding a column, we lock the header row of its parent and all its children. Then we propagate the add column to all the child views. If you're adding a column, we need to make sure that there isn't an existing child that has the same column, that has a different data type, for example. So if we detect that, then we fail the add column, saying that there's a conflict. So we also have checks when we drop a column. Let's say you're dropping a column in a parent, and there's a child view that was created that uses the column. Then we'll throw an exception saying you can't drop the column. Also, if you have a view index that requires the column being dropped, then we will drop the view index along with dropping the column. And if the column is a covered column in the view index, and we just drop the covered column in the view index table. And so if you drop a table that has child views, if you don't specify the cascade keyword, then the drop will fail. If you specify the cascade keyword, then we'll go and drop all the child view metadata as well. So the reason we can do all of this is system.catalog is on a single region, so we can lock rows, lock all the child views, the child view header rows and the parent header rows at the same time. So here's a concrete example. So if you look at, if you consider the queryable report use case that I spoke about earlier, we have the base table report instance, and let's say you have two reports, one on opportunities and one on accounts. And if you wanted to add a column created by to the base table, first what we do is we lock the base table, then we lock all the child views, and then we actually propagate, and then we actually call mutate rows, region.mutate rows to atomically add the mutations to the child views and to the base table. So since the header rows are locked when you're adding the column, if there's a conflicting change that happens, so let's say somebody else is trying to add the same column with a different type, or another client is trying to create a view or create an index. Since we lock the header row for the views and the base table, the conflicting change will fail. So if we allow system.catalog to split, we can no longer lock a parent table and a child view rows because they could be on different regions. So we need to handle, main case we need to handle is how to detect conflicting changes and prevent them from happening. So what we do is, before we send a mutate column request, we do a check-in mutate and the row key so we try to write a cell with the row key that basically contains the column name. And so if you have multiple clients trying to add the same column or mutate a column, only one of them will be able to do the check input, and one of them will be able to make the request to the server. And we use when we do the check and mutate, we use a TTL of a short time, around 15 minutes. So in case the actual request fails for any reason, the client can retry at a later time. So before making the request, we do this check and mutate. Then we actually make the request to the server. On the server side, we'll just lock let's say you're adding a column to a parent table. We only lock the parent table. We don't lock all of its children. We apply the metadata changes just to the parent, and we don't propagate metadata. We don't propagate metadata changes anymore to any of the children. So now, when a view is resolved, we need to resolve all of its parents and add the columns of the parents to the table that's returned for the view. And then we do all the same add and drop checks as we used to do as before. So drop cascade is similar. We don't drop. So we only drop the parent table. We don't drop any of the child views, and we only remove the child view metadata during compaction. And if you retry to do here's an example for the multi-region implementation of adding a column. So the same example as before, you have the base table report instance and 2 child views. Before we try to add the column created by, we do a check input. And if we successfully write the cell, then we make the request to the server to add the created by column. On the server side, we'll lock just the header table, just the rows of the header table report instance, and make the changes and apply the metadata changes. So at the same time, if some other client tries to add a column with the same name, then it will fail because it won't be able to do the check and put. But if you want to add a column with a different name, then that will succeed. So let Rahul go into some more details about the implementation.
No? Okay, there we go. Okay, so I'll start off, and I have a few slides here. Unfortunately, Thomas and I didn't get to meet, so if I'm repeating something, I apologize. And so, as with most things, I started working on this feature, and then I didn't finish it as usual, and Thomas took it all the way. So I'll talk about like why we chose this approach and what were the reasons behind it. It'll just be pretty quick. So why did we choose this approach? We needed backwards and forwards compatibility. We didn't have the availability of transactions at the time, like OMID, and we didn't want to introduce like an external locking kind of dependency, like on Zookeeper or HDFS. And so let's see. And the current implementation uses like row-level locking, as Thomas had talked about, to keep consistency between relationships. But with multiple regions on different servers, we can't take advantage of this anymore. So another solution is necessary. So the key design is everything. So the first thing you're probably thinking is like, well, why didn't you choose a split point in the system catalog table and make sure everything that's related to each other is in the same region? And we couldn't do that because schemas prefixes like the table name and the view name, and you could have views can be on different schemas. So we can't control, they're not basically contiguous on the table. So that became a problem, and it would have been ideal if we could have just chosen a split point and kept all relationships in their own region. Then we could have used this relationship. So, whoops. Sorry, I was thinking this was up there. How do I? Can you change the slide to? Sorry, Thomas.
This one.
figure out next one. There. Okay, cool. Thank you. So instead of locking your children with in-memory row locks, now you just simply add the column and all your children will just resolve on read. So how does it work? We have to take care of the three basic scenarios: add columns, remove columns, and drop cascade. So currently, if you have a physical table A with a child view B, if you add a column to A, you'll lock both the physical table and the view, and to both entities on their respective rows. So we need to do this without this locking dependency on both, so we can span multiple regions. So can you go to the next slide? Thank you. All right, so we had to have a new link type, because every time we do a read from any entity, we basically read that entity and then traverse back up to the parent, which is the base table in Phoenix. So, and to keep backwards and forwards compatibility, what we do is we remove like any duplicates on the way up, so an old client and new server can read together. So we only store metadata about the view itself. So if you have like a parent table with columns A, B, C, and you add a column D, the view only stores D now. It used to store A, B, C, and D before, but now we only store what's different about the view, the delta. So, sorry, it's locking up on me. So but you're thinking like, what if client 1 adds column Z to the parent table, and what if client 2 adds column Z? So initially our design was with timestamps, but but when you have clock skew, that won't work. So then they came up with the check input afterwards. So can you go to the next slide? So how do we drop columns, you're thinking? So the way to drop columns is, for deletes, we created the new link type called, it's called an excluded column. And so if you take the example I gave you earlier, the table that has columns A, B, C, where the child view has columns A, B, C, D, and you want to drop C from your child view, you can accomplish this by just adding that information in the excluded column about the view itself. So all you'd add is a excluded column C in the view itself. Then when you walk up the tree, we just create a list of columns. And if that column is contained in the parent as well, we'll see the one that's there. So basically what you're doing is you're saying what I'm going to exclude from my parent in myself. And so can we go to the next slide, Thomas? Yes, drop cascade. So Thomas had already mentioned this earlier. So we only delete the table view reference in the drop. So whenever we read, if there's like a hole in the chain as we're reading up, that means it's gone, and we return a table not found exception. And then we clean up anything with a hole later on in compaction. And so I guess they wanted like someone with a pulse to come up here and give that information, but now I'll go back to Thomas.
Yeah. So just one thing about drop cascade. So since we don't clean up the metadata of child views, if you try to recreate a base table that was dropped, then we detect that. Then at that point we have to delete the metadata from the child view, or at least try to delete it, or else if you recreate the base table with the same name, you'll automatically get a bunch of children. Okay, so then I'll just talk about a few metadata optimizations that you can use. So update cache frequency. So all of these are basically table properties. So let's say you have a base table metrics base that is used to host OpenTSDB style metrics. So it has two PK columns, metric ID and metric type, and then the metric value. Here we have these table properties. So append-only schema is set to true, update cache frequency is set to never, and auto partition sequence is set to metric ID. So we'll go into detail about what these actually do. So Phoenix has a client-side metadata cache that is shared across all Phoenix connections. And the update cache frequency is used to determine the frequency at which RPC is made to the server, to system catalog, to fetch the latest metadata. So you can, the values that you can set up with cache frequency are either always, which means it will always hit the server, or never, which means if it's in the cache, it's never going to hit the server again. Or you can set some time in milliseconds. And point of doing all of this is if generally you don't update your schema, then you don't need to keep pinging the server and checking if there are any updates. So that reduces load on system catalog, and it will improve your query performance. There are a few limitations you need to know while using update cache frequency. If an index becomes disabled, clients will still use the index until the update cache frequency expires. And also, if you drop a column, clients will still see column values until delete markers are placed for the column being dropped, or the update cache frequency expires. So auto partition sequence. So so in the example here, we have this metric ID, and generally when you create a view, you create the view and you select a subset of rows of the base table. So you'll filter on metric ID. So so let's say you wanted to create two metrics, CPU time and search results. What you have to do is create the view with the columns and then say select star from metric space where metric type is equal to 1 or metric type is equal to some number. So instead of doing this, if you set that auto partition sequence to a sequence name, then it will just, when the create view DDL is run, you don't need to specify uh, the integer value that's used for the metric ID. It will automatically fetch it from this sequence. So this is just basically just a convenience feature. Then we have the last thing is append-only schema. So if you mark a table as append-only schema true, that means you can only add columns but never drop columns from the table. So what this allows us to do is so let's say you're doing a create view if not exists, and if the view already exists in the cache, then you don't need to make an RPC to the server, because if your create view statement includes all the columns that are already uh, if all the columns in your create view statement are present in the p table in the cache. So if you're adding a new column at that point, you need to just add the new columns and then you make an RPC. This kind of helps us, with using views for implementing like OpenTSDB style metrics. So every time uh, let me go on with the example. So let's say you have the search results metric, and these user and query columns are similar to tags in OpenTSDB. And let's say you want to add another tag, then if your cache doesn't contain that column, then you need to make an RPC, or else you don't. So it just improves performance when you use this to store time series style data. The other thing that append-only schema does is if you mark a table as append-only schema true, then for immutable data, it will allow you to use our immutable storage format, which stores all column values of a column family in a single cell instead of one cell column per column value. So this will, using the storage format, there was no way to use the storage format for for multi-tenant data before, but if you mark the table append-only schema true, then you can use it for multi-tenant data, and this will improve your query performance a lot and also decrease the space taken on disk. I think that's all I have. So, any questions? I think the mic isn't hooked up to the. Uh, I couldn't actually hear the question. Maybe Rahul, can you repeat it?
The audio guy just stepped out. You want to come up here? Just talking to the computer.
Oh. So my question is there any are there any limitations in terms of number of tables, a number of inheritance that each view can have? Like I saw you have inheritance in your implementation. And are there
Yeah.
any limits for the number of inheritance that can be there?
Okay, so the question is, are there any limits to the number of child views that a parent can have? So there are no limitations. You can have millions of views defined on a base table.
The second question that I have is about the region server that you mentioned. Uh, are there are you serving your clients cross regions, or is just each client goes to one region?
Uh, so, you mean like
Suppose that there is a data of each client is stored in one region, like you have multiple regions, and
yeah?
is a region per client, like for serving each client, you just need to scan the data in one region, or if there's any failover, you can go from region to region, or you basically can load balance across the region, so you can utilize all of your environments.
Oh, I see. So, let's say your view metadata is on a particular region. If that fails, then it's like how if any region in HBase fails, we just rely on HBase to handle all of that. Um, the region gets moved to another region server, and then for a brief period of time, you won't be able to access the metadata of that particular view. But once it's live on the new region server, then you'll be able to access it. So it's just how any other regular HBase table works. We don't do anything special. So system of catalog is just a regular HBase table, basically.
Okay, I think we're done here, Thomas. Thank you very much for your time. I'm sure it's really late there.
Yeah, it's really early, actually. Thanks.
Thank you very much.
Thank you.